In this lesson, I'm going to discuss the set builder notation, which is a convenient way to build sets out of other sets. Now, the general idea of the set builder notation is that you have to look at every single element in the original set, and then you have to check whether or not that element satisfies some condition. So just to read this one more time, the set builder notation builds new sets from old sets by checking whether each element satisfies some condition. Elements that do are kept in the new set. Suppose you started off with some set X, and I've drawn the elements in the set as little pieces of candy. And then I've drawn this new machine over here. I want you to imagine that the role of this machine is to look at each individual element and decide whether or not it will keep it for the new set. I then made an exact copy of this machine below, just so that you can see what happens to more than one element. Now after this, I want you to imagine the new set that we're building on the right hand side. Okay, so these machines are designed so that they only allow elements with cool colors to pass through. So for example, these colors over here are cool colors. The machine will also let the purple and the green term through to the new set as well. On the other hand, every other element does not qualify as a cool color. So for example, if you put this yellow through the second machine, which is identical to the first, this is actually going to fail and it's not going to be included in the set. Okay, so now that you get the general idea, let me introduce you to the actual notation. The set builder notation is usually written like this. So to read this to you directly, Y is the new set filled with a whole bunch of new elements such that each of those elements passes every condition in the condition list. Now, most commonly, you're going to be building new sets from the real numbers or from other numeric sets. So in those cases, we would write it like this. So this set Y is built from a whole bunch of elements which we're going to call X. We say that for every X, we expect each one to be a member of the real numbers. Remember, the way we read this is that X is a real number. And then we expect X to satisfy every other condition in our condition list. There is another popular notation that's just designed to save you a little bit of time. Instead of putting X as an element of R over here, instead we write it over here. Because after all, to build a new set, you have to start with an old set. So to read this one more time, we're saying that Y is a set where each element, which we call X, is in R, such that every single one of these conditions is satisfied by the letter X. Before I show you some examples, I just want you to know that sometimes, instead of seeing a vertical bar, some authors prefer to use a colon. That's perfectly okay as well, and if you'd like to do it, feel free. Now, just in case you're unsure of how this picture on the left ties into this on the right, I just want you to realize that this machine is kind of the thing that's in charge of making sure that every element passes the conditions. But this will be really clear when I show you some examples. So this problem asks us to build the set of all even numbers. Now the way we're going to do that is we're going to start off with a set of integers. And then after this, I want you to understand that we want to make a new set that contains only even numbers. And this one of course does contain a whole bunch of odd numbers that we don't want. Well, one thing we can always do, if we have an odd number, is to just double it. If we double odd numbers, they turn into even numbers. So therefore, if we took some random element in the set of integers, if we say that this randomly chosen element is going to be called X, then doubling X is always going to give us an even number, no matter what integer we start with. So if we double negative 3, we're going to end up with negative 6. If we double negative 2, we're going to end up with negative 4, and so on. Now, one of the cool side effects of this procedure is that you notice that 0 must actually be an even number. I'm not sure if you expected that, but I certainly didn't initially. Okay, but then the next question is, how do we actually build this using the set builder notation? Let me go ahead and show you that too. So using the set builder notation, I want to say that E is the set of even numbers again. I have just written the such that bar, and we're going to try to figure out exactly what to put where. I want to start with every single number that is an element of Z. So let me write that X is an element of Z. Now, as we said before, if you choose a random element in Z, such as this X over here, it's going to correspond to this element over here, which is going to be 2X. So therefore, the new element you're after is going to be 2 times the old element that you started with. So therefore, the set of even numbers can just be written like this, and that's pretty straightforward. But I want you to notice that we didn't really need to deal with any conditions. The only condition is that the X we started with had to be in Z. So for example, if you started with X equal to 3.6, then this condition would fail and you would not actually put that number in the even numbers. The fact that you've written 2X here means that you've replaced your X for a number which we're going to call 2X. Now, because this example didn't have any other conditions, it isn't a really interesting example. It's really just meant to be a warm-up. But how about I give you another example with some conditions? So we just built the even numbers, but now we want to build the odd numbers. I want you to understand that if you started off with an even number and then added 1 to it, you always end up with an odd number. Now, we could actually build the odd numbers from the even numbers, but instead I'm going to do it from the integers again. So again, I've written out the list of integers, but I want you to imagine that we pick some random number, which again we'll call x. We know that if we replace x for 2x, we will end up with even numbers. So let me write that as well. 0 times 2 is still going to be 0, 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, and so on. We also see that 3 gets replaced for 6, so we can also say that x gets replaced for 2x. So this 6 represents 2 times the number you started with. Now, as we said, to make the odd numbers, you just have to add 1 to every even number. So if we do that, 0 will map to 1, 2 becomes 3, 4 becomes 5, 6 becomes 7, and so on. Now, if we look at this carefully again, I want you to notice that 6 has mapped to 7. So that means 2x has mapped to 2x plus 1, because 7 is 1 more than 6. So now at this stage, we have the odd numbers, but we don't have the odd numbers between 3 and 10. That's where our little machine comes in. It's going to go through every single element and decide whether or not that number is actually between 3 and 10. So this 1 is going to get left out, this 3 is going to stay, the 5, 7, and 9 will stay, but then this 11 is bigger than 10, so it's going to get left out as well. Now, no matter how far you go left or right, no other element is going to be between 3 and 10. So therefore, O310 contains the numbers 3, 5, 7, and 9. Now, to write this out using set builder notation, we just do the exact same thing. So this time, we again start with x being a member of Z. So we start by writing that x is in Z. Now, as we said, the set of odd numbers starts off with an element x, that's for sure, but eventually we end up with elements that are 2x plus 1. So for example, if we started with the number 2, we would end up tracing that number to the number 5, which you can make by doubling 2 and then adding 1 to it. So another way to read this is, if you started off with any integer x, if you multiply that integer by 2, then add 1 to it, you are guaranteed to end up with an odd number. But to make sure that that odd number is between 3 and 10, you need 2x plus 1 to be between 3 and 10. So that's actually the other condition we have to add to our list. And therefore, to write out the odd numbers between 3 and 10 using the set builder notation, you'd write all of this. Now of course it is actually easier in this case to list out all the numbers this way. But in many cases there will be so many elements in the set that listing out the set explicitly ends up being a lot harder than just writing it using set builder notation. I'm sure you'll see a lot of examples like that as you study more and more mathematics. This is a very easy case, but the set builder is hard. But usually the set builder is going to be easier and the actual explicit set is going to be harder. Now that just about completes every example I wanted to show you, so let's just summarize the lesson. In this lesson, we talked about a convenient way to build new sets from old sets, which we called the set builder notation. we said that to use the set builder notation, we would write every new element in our new set y in terms of our old set somehow. Given an element in our original set, we use a condition list to test whether or not to admit that element into the new set. If it passes the condition, we keep it, and if it fails the condition, we throw it away. It's possible to list as many conditions as you like, separated by commas. And for an element to make it from the original set to the final set, it actually needs to pass all of the conditions, not just one of them. We also said that the most common use of the set builder notation is to build new numeric sets from old numeric sets. And the way we do this is we write it out in either one of these two formats. In the top format, we're saying that y is built from the real numbers, and we're saying that x is an element in the real numbers. We only keep x if it satisfies all of the conditions in our condition list, as well as the fact that it's a real number. Now, as you saw in the examples, specifying things this way is actually really useful, because it allows you to construct new sets by actually changing the elements in the new set. But most of the time we don't actually change the elements in the new set, and in that case we could just write this condition on the left-hand side, and you'll see that done pretty often as well. And finally, we said that some people like to use colons rather than vertical bars, and if you see that, don't get confused. Now, unlike this set over here, the set builder notation is really useful because it allows us to talk about sets that we cannot write out explicitly like this one on the left. But you'll definitely see that as you do more and more examples. But that just about completes everything I wanted to say about the set builder notation. As you learn more about numeric sets, you'll see why this set builder notation is super useful. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.